Is the screen visible to you all?
Hmm.
Okay, so let me start.
Yes, ma'am.
Yes. Uh, the experiment is on the verification of superposition and Thevenin's theorem. Already it has been discussed in your class, theoretical class, and we hope that you know what is superposition theorem. So here also we will again explain this, and then we will move to the experimentation, to the video recording of the experiment that we did in the laboratory, and we are going to demonstrate this to you. So according to the statement of superposition theorem, in any linear bilateral network, linear means it obeys the homogeneity and superposition principle, and bilateral means current can flow in any direction. In any direction means obviously in forward and backward direction, whatever uh, in direction in the network, and the current at any point on the network should be the algebraic summation of the currents uh, currents when each of the sources are considered individually, and their effect will be summed up, will be the resultant effect of them will be the net current flowing through the network, or flowing through any point of the network. And if the it obviously the network is assumed to be have more than one sources. Okay, now superposition theorem is applicable for DC AC both the cases, both the network, and it is not only for the current flowing through any point in the network, but also it is applicable for measurement of any measurement of voltage across any two terminals or across any branches of the network. Okay, so the resultant summation when all the sources are taken are considered is the effect of is the algebraic summation of the individual effect of the sources. Now here, first of all, the linearity property we will explain to you. Linearity property is the property of an element describing a linear relationship between cause and effect. So suppose a voltage is applied in the network, and current is the effect. So current and voltage, this two maintains the linear relationship. It's like V is equal to IR, right? Achha. Where R is the constant. And another thing is that the property is a combination of both the homogeneity and additive property. So additive property means here suppose X is the cause and Y is the effect. X1 is the cause, Y1 is the effect, X2 is the cause, Y2 is the effect. So suppose alpha x1 plus beta x2 is applied, is the cause, then the output will be alpha y1 plus beta y2. See here it is written in equation form. Suppose V is the cause and I is the effect. So suppose Kv is applied, then the effect will be Ki. Here V1 is equal to I1R and V2 is equal to I2R. So the net effect when I1 plus I2 is the cause, then what would be the effect? Effect will be V1 plus V2. Achha. So resistor is a linear element. Not only that, inductance and capacitance are also linear elements. Achha. Now, can you give any example of uh, unilateral network? And resistance, inductance, capacitance both are also uh, Bilateral. Can you give any example of unilateral element?
N junction diode.
Diode. Diode.
Yes. 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 Good. 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 Acha. Now, what actually we are going to first verify the superposition theorem. The network that we will consider over here consists of three resistances. What are the three resistances? R1, R2, R3, and here we will consider two sources, VA and VB. Okay, so the current due to this due to these two sources are I1, I2 and I3 flowing through the resistances R1, R2, R3, or you can assume that through these branches AB, BC and BD, the current I1, I2 and I3 respectively are flowing. So what is our objective? We will check here whether this I1, I2, I3 are the algebraic summation of the currents when V1 and VB are acting individually or separately. So for this case, you refer the figure 2A and 2B. In 2A, VA is acting only where the VB is replaced with its internal resistance. Understood? So that's why it is shorted. Ideally, it is assumed to be have the zero internal resistance. So that is omitted and this one is shorted. On the other hand, when VB is considered only, then this VA part will be shorted and assumed to be zero internal resistance. So you see in the branch AB, when VA is acting, I1A is the current, and when VB is acting only, then I1B is the current flowing through the branch AB. So according to superposition theorem, if it holds good, then what will happen? I1 should be close or should be equal to or close to I1A or plus or minus I1B. Can you tell me which one will be applicable here? I told you algebraic summation. See here when minus because VA acting means current is flowing through this direction and VB acting current is flowing through from B to A. So therefore this will be obviously minus. So I1A minus I1B. For this case, I2A minus I2B, current direction opposite. Whereas through BD, you see what would be that? I3A
Plus I3.
plus I3B will be equal to or close to this I3 if superposition theorem holds good, right? And we will demonstrate it. So see here what I have discussed to you just now, it is written. Now for experimentation, it is very important that what would be the instruments or what would be the elements we are going to have. We are going to use here. Okay. So for the two voltage sources VA and VB, we need to supply VA. It is 0 to 10 volt and VB is 0 to 30 volt, right? Next is 3 ammeters are required to measure current flowing through AB, current flowing through BC and current flowing through BD, right? So this current this ammeter should have the rating, should have the capability to find out the current to have the range which in tune with the current flowing through this AB, BC and CD. Otherwise, you will not get the proper reading, right? Next is 3 resistances are required, R1, R2, R3. Here we are not measuring the voltages for the time being, so no voltmeter is required here, right? So here we will show you exactly what is the value of V and VB we have considered, that we will show you during the recording. Acha. So, Arthur sir, may I start it?
Yes, madam. And you can brief down the explanation because they have I mean, so many times acquainted with these theorems. So explanation part is
Not required.
not that much required. Briefly, you can tell and then play the
Okay,
video.
fine. Oh, acha. First, let me stop the sharing, and then I need to include computer sound, na?
Mm-hmm.
Good afternoon, students. Today we are visible and audible. The network theorem 1, that is
Yes,
Yes,
ma'am.
ma'am.
theorem.
Ma'am,
Yes,
could you
ma'am.
just increase the volume a little?
Superposition theorem. We are having the circuit as shown in this figure. Can you see this figure?
Yes,
It
ma'am,
is
it's
having
okay.
three resistances with three ammeters, which are used to measure the current of these three branches. That means current flowing through this R1, R2, and R3. And there are two sources are connected over here. One source is this, another is this. Acha. You can see here in the experimental setup, these are two sources. This is the first one as shown over here, and the second sources is this. Now you can see here the first sources is showing 7.7 volt, which we are keeping, and here the second source is 5.5 volt. Okay, now I'm coming to the connection. What is the connection? First of all, you can see over here this A point is coming here and this is coming here. So we are giving the sources here across this two terminal. This two terminal is this. Now next is ammeter and this resistance. These two are in series. So what we have given, this is coming over here, then resistance, then resistance is these two are in series, resistance and ammeter. You can interchange the position. So first we are keeping the resistance, then the ammeter. So next this one is coming to the ammeter, and the ammeter from the another terminal of the ammeter, it is going to the next branch, that means this B point, right? So here it is the B point, right? So across this B and D, this is D point, this resistance is connected. This resistance, you can see it, this one is the rheostat. Here intentionally one rheostat is kept to show you how the rheostat is being connected. So it is the variable terminal, and you can see over here, this is
This
the
is the other
fixed
term, fixed
other
term.
terminal. Okay. Now B terminal. Now from B terminal, what it is coming here. Okay. Now from this, it is going to this resistance R2, right? R2. Then from the other terminal of R2, to measure the branch current across R2, another ammeter is connected. So this one is the second ammeter. So this one is the first ammeter, which is measuring I1. This one is I2, and this is I3. So from the another terminal of the ammeter, it is going to the source. So you can see over here, it is going to the source, and the other terminal of the source, from the other terminal of the source, here it is connected here. So this point is next. Now to additionally here two resistances are kept, that is 30 ohm and 30 ohm. No need to worry about it because the same current is flowing over here. Now from across this terminal, it is going to here to measure the I3 branch current, and from the ammeter, this terminal, it is going back. Okay, so this three terminal again connected. Understood? Achha. Now we are going to demonstrate the procedure. First, what we will do, when two sources are connected, this is the case when two sources are connected, we will measure all these three currents, I1, I2, I3. So here I1 is showing 0.04 ampere, I3 is showing 0.06, and I2 is showing 0.02. So therefore I am writing over here I1 is 0.04. I am not writing the unit over here, I am writing over here. This is ampere, so 0.02. And this one I3 is 0.06 when both the sources are connected. both the sources. Let me proceed to the second run. What is that? When only V1 is connected. So that means we have to short the V2. Let me short it. Okay. Now I am making it off. Every time you have to keep in mind that you have to make it off, and then we will do this. Now how I am doing this? Let me open this and see, this source is just isolated. Okay, removed. Now we are going to have the next set of reading. That means V1 is connected only, and we will measure all these three currents. So now I am making it on. Sorry.
If required, we can switch it.
We can switch it off. Now these are the measurements. That is I1A. Next is I2A, and this one is I3A. Okay, so let me write it out. I2A 103. So this is DC current. You can see the negative sign. That means current flowing in the opposite direction. What we have assumed previously, this current is just the opposite direction. Okay, and it should be, because if only this source is connected and this source is not connected, so therefore the current should be in this direction. But previously when this source is connected, the current is in this direction. That's why this is negative. Okay, there should not be any confusion regarding that. So that is when V1 is connected only. Now only one run is left, that is V2 is connected only, which will gives us I1B, I2B and I3B. Now let me redo the process. First, I am connecting the V2 again in the circuit, in the network, and then I will remove V1 from the network. Look at here, it is being shorted. V1 is shorted. That means we are removing this one. Okay. This 2 points shorted. Now I am making it on. Remember that V1, V2, V3 value should not be varied during the whole experiment. Okay. Now let me measure. This one is I1B. You see, it is flowing in the opposite direction with respect to the previous one. This is I3B. And that is I2B. All are in ampere. Now we are going to verify the superposition theorem. How? I1 should be equal to or close to I1A plus I1B. Acha, I1A is 0.06 and I1B is minus 0.02. What it is coming? 0.04 ampere. And look at here, I1 is perfectly 0.04. So we can write it here, verified. Right. Next is I2A and I2B. I2A is and I2B is 4 ampere and I3A and I3B. I3A is 3 ampere. Now look at here. I2 is 0.02 and this is 0.01. That means it is close to this. So here also we can write it verified with little error. Similarly, it is 0.05 ampere and here it is found out to be 0.06. So here also these are close to each other. So therefore here also we can write it as verified. So with all this with this experiment we can say that superposition theorem is verified here perfectly and in this too with little error. So in a nutshell we can say that this is the superposition theorem is verified satisfactorily. Okay, student. Hello. Hello.
Yes, ma'am.
Yes, ma'am.
Yes,
Okay.
ma'am.
Yes, ma'am.
So can you tell us that what are the why this little bit error are coming?
Because of the internal resistance of the voltage source.
Yes, internal resistance may be due to some precision error in the instrument part. So because of that only this errors are coming. Achha. Now see here the table. In the table you can see, let me show you that this is the previous one when both the sources are connected. This 3 when only one source is connected, first source. Achha. Although I told you in during experimentation that V1, V2, but actually these are VA, VB. V1, V2, V3 are the voltage across the 3 resistances. Remember that thing. And another thing I mentioned that V1, V2, V3 should not change. It is not the voltage across the resistances. It is talking about the input voltage sources magnitude. Understood?
Ma'am.
So this hello?
Ma'am, I1 equal to I1A minus I1 B ना ma'am.
Which one?
उसमें ma'am I1 और I2 में ma'am.
This one.
Yes ma'am. I1.
I1 is equal to E1 should be I1A plus I1B, I2 should be I2A plus I2B, I3 should be I3A plus I2B.
Minus ना ma'am. I1A minus
No.
I1.
Actually, during experimentation, we have written in terms of plus and minus. That's why.
We are finding
Okay.
algebraic sum, na?
Algebraic summation.
You just note the symbols here.
We have not written like that. I1B is equal to, we have written I1B is equal to minus of that. So minus is considered in its, in it
Yes.
already. That's why. I1B is found out to be what? Minus 0.02. Isn't it? Hello?
Yes ma'am. Yes ma'am.
Okay. Achha. Now, your task is that we have assumed R1 30 ohm, R2 30 ohm and R3 100 ohm. And already you have noted down that what is the VABB value. So with this VABB value, you first consider both sources, find out the I1, I2, I3 and next you take separately VA and VB and find out this currents and check whether it is coming out, it is verified or not. The superposition theorem is verified or not. That is the task left with you. Clear?
One thing here, maybe R3 is not 100 because we have taken all three are same, na? Or no? No. We have taken rheostat there, I think.
Rheostat there. Rheostat.
Okay.
It may happen that this is not same as this. The current you are finding, current you will find, this should not be same as that. It may happen. This is due to this resistances values. But for this case, you find out the separate individual currents that will differ also. Clear? So that part is left to you. Next, can we move to Thevenin's theorem? Hello?
Yes, ma'am.
Yes ma'am.
Ma'am.
Hi, yes.
What did you say? What we need to do? I could not hear it. Could you repeat?
Yes, obviously. We are here to repeat it several times if you cannot understand. VA, BB voltage sources. Already we show you VA and VB value. Can anybody tell us what is the VA and VB value we have shown to you? What is the VA value? 7.7
and 5.5.
5.5. So with these two voltage values and this R1, R2, R3 like this, find out I1, I2, I3. Fine. Acha. Now you omit VB. Having VA only, find out I1A, I2A, I3, I1A, I2A and I3A. Very sorry, just 1 minute. 1 minute. This is not I3B. This is I3A. Huh? Very sorry. Just wait for a minute. Huh? So find out I1A, I2A and I3A. Next, just do the opposite thing. Include VB 5.5, omit VA and find out I1B, I2B and I3B. And now you verify whether this algebraic summation is coming out to be the coming out same as I1, I2, I3 or error exists. Clear? Clear?
Ma'am,
Yes,
yes, ma'am. What you said about R3 is equal to 100 ohm, is it 30 or 100? R3.
You take it 100. No problem. No problem at all. Clear? No problem at all. Because all value changes accordingly.
Ma'am, this we'll write in the practical
Report.
writing. Yes, ma'am.
Yes.
Okay, ma'am.
Next, I am moving to Thevenin's theorem. So here, Thevenin's theorem states that any two terminals of a network composed of linear, passive, and active elements may be replaced by an equivalent voltage. Suppose there is a network which is having several resistances, inductances, capacitance with a voltage source. Then the same network can, and with a load connected across it, we can replace that with a single voltage source in series with its equivalent internal resistances and with the load, and we will find out the load current accordingly. So this will be the equivalent to each other, this two networks. So any two terminals network may be replaced by an equivalent voltage source in series with an equivalent resistance. The voltage source is equal to the open circuit voltage. That is very important. Open circuit voltage between two terminals, and the series resistance is the equivalent resistance looking back into the network through the terminal, with all the sources within the terminals are replaced by their internal resistances. So here we are going to consider.
Ma'am, I have a question.
Yes.
Ma'am, in the practical, everything we are writing in our own language, but the theorem should stay as it is, right?
Yes. Theorem should be whatever be written by the people who have written this actually. We cannot change it. The explanation can be in your own words, but the statement
you can paraphrase anyway. But the sense should be same. I mean, the concept should be same, right?
Yes, we don't have
to
any
some
problem.
extent. To some extent, the language may change, but the essence should be intact.
But when
like looking into the terminal, that you cannot change.
Yes,
and
that will actually lose the essence. But ultimately, when time flies, we will ultimately be habituated with the statement, because each and every word will be are meaningful here. we will when we started during our undergraduate program, undergraduate courses, this type of statements, we were that time also thinking that we should not write whatever be written exactly follow this, but ultimately we became habituated with this. Now we are afraid that whether we are losing any meaningful word or not, huh? So that happened. It
So
will
better to
also
follow what is given.
what is given. Acha. So here it is the bridge circuit, huh? And voltage source is connected across this BD terminal. So the the P resistance P is connected across AB, Q connected across BC, S connected across DC, and R connected across AD. Now the load resistance is connected across C and A, and the load resistance, so variable load resistance, is connected here. This is RL. Now this circuit can be replaced with this equivalent, where Thevenin is the equivalent voltage source in series with an equivalent voltage, equivalent resistance, and this RL intact, right? Now, what is that Thevenin? That already told to you by the statement that looking back into the network through the terminals, across which the load is connected, back into the network. Okay, so here if you see this, what would be the equivalent, and this VIN will be replaced with this with its internal resistances, and ideally it should be 0. So we can think of it's a shorted. So BD will be shorted here, and we are finding out the resistance across CA. So can you tell me what would be the resistance is there for? If I am drawing this,
Ma'am, it will be R P parallel R plus Q parallel.
BD shorted, right? Achha. This is A. Understood? AB. This. Am I correct? A,
Yes,
C,
ma'am. Yes,
B.
ma'am.
So what does it mean? BD shorted means this P and R will be in parallel to each other, and Q and S will be in parallel to each other, and therefore, and this two will be in this equivalent will be in series. So P parallel R plus Q parallel S. Am I correct?
Yes, ma'am.
If
Yes,
these
ma'am.
resistances are known to you, you can find it. This. Okay, fine. Achha. So to verify Thevenin theorem, what we will do, we have uttered a term open circuit voltage. That means opening this, that means removing RL, we will find out the voltage across AC, and that would be our Thevenin, right? See. So if we put here a voltmeter, so that voltmeter will gives us the reading of Thevenin. Am I correct? Am I correct?
Yes,
Yes.
ma'am.
Achha.
Yes, ma'am.
Then how to measure Thevenin? Achha. Thevenin, that already I told you, I have discussed with you Thevenin, how it would be. Huh? So in experimentation will be done how? That the process is that first of all, here Thevenin is the equivalent resistance looking back at the terminal that I told you. Now we have from this, let me show you. According to this, suppose this is the current IL is flowing through RL. Since these two are equivalent, so this IL should also flow, isn't it? Achha. Now look at here. We can write it like this. According to KVL, following KVL, IL Thevenin plus RL IL, or we can write it as VL, voltage across the load resistance. Am I correct? Hello,
Yes,
am I?
ma'am. Yes, ma'am.
Because we don't know exactly the value of RL. So better we keep it as VL. So VThevenin equal to IL RL IL RThevenin
Plus VL.
plus VL, right? Or VL is equal to minus RThevenin IL plus VThevenin. Am I correct?
Yes, ma'am.
Yes, ma'am.
Isn't it? Acha. Remember this equation. So this, that already, sorry, let me take the pointer. VL equal to minus RThevenin IL plus VThevenin. So with varying RL, since we have taken up what should I say, rheostat, and we can vary the position of the jockey to vary the load resistance RL, and we can have a plot VL versus IL. Am I correct? Or IL versus VL. Correct? Achha. Now,
Yes, ma'am.
achha. So say this is the plot here, y-axis VL and x-axis IL. Correct? Achha. We will find out, you see from here, y is equal to mx plus c. Y is equal to mx plus c. Am I correct? In this form only? Hello?
Yes,
Am I
ma'am.
correct? Achha. When
Yes.
x is 0, y is equal to c. And c is here VThevenin. So this point 0 comma VThevenin. Zero comma VThevenin. Achha. Similar way, when VL equal to 0, then what is IL?
VTH by RTH.
VTH by RTH. Achha. One more thing. When VL 0 means voltage across the RL is 0. What does it mean? It is short circuit. Am I correct? Am I correct? That means
Yes, ma'am.
RL equal to 0 at that point. RL equal to 0. So we can name this as I short circuit. So short circuit current, comma 0, since VL is 0. Okay? Acha. Now look at here. The aim is minus RThevenin. Am I clear? Am I clear? Aim is equal to minus RThevenin. And you can also look it from here, 2 points, a straight line, pass. If we can extend this, it will intersect with the y-axis at this point, which is nothing but 0 comma VThevenin, and it will intersect with the x-axis at ISC comma 0. So we are getting 2 points. So y-axis, y coordinate is VThevenin here, and here it is 0. So VThevenin, so aim will be equal to VThevenin 2 points. So VThevenin minus 0 and divided by 0 minus ISC. Am I correct? So what is that? Minus VThevenin by ISC. Am I correct?
Yes, ma'am.
That is aim. So RThevenin, aim is equal to minus RThevenin, and RThevenin is therefore VThevenin by ISC. So one can easily find out, if you know the VThevenin and if you know the ISC, you can easily find out the RThevenin. Okay, so VThevenin is nothing but the open circuit voltage when the load resistance is opened, it is removed. Okay, And ISC means it is nothing but the short circuit current when RL is 0. It is shorted. 2 points across which the RL is connected is shorted, right? So here we will show everything to you and we will verify whether it is coming or not. Okay, see. First of all, what we have done in the experiment, that RL we are going to vary. We are measuring the voltage across this RL, which gives us VL, and the current flowing through RL. So this ammeter gives us the reading of IL and this voltmeter gives us the reading of VL. Agree? Achha. So here we will take several points with different values of RL, and one of the point obviously should be RL equal to 0 and another point RL removed. So when RL equal to 0, it will gives you I short circuit, and when it would be open, it would give you the voltage. The VL voltage will give you the V Thevenin, right? Achha. So here, by a digital voltmeter, measure the voltage VL across RL, calculate the load current according to the above equation, or you can directly measure it. Gradually decrease RL till the lowest supplied value is exhausted. For each RL, we have to keep the V input constant. And the input voltage will not be varied, it will remain as it is. So plot VL versus IL graph and find the intercept VLO, that means V open circuit or V Thevenin, and the slope R Thevenin from the straight line graph. Measure the open circuit voltage V Thevenin at the terminal CA and keeping VIN unchanged. So it is seen that VLO, when the intercept that we will found graphically and what we will find out experimentally should be same, then only it would be verified. I'll remove the load resistance RL and connect the terminal CA by an ammeter and measure the short circuit current. So how we will measure the short circuit current? You see, it gives you the open circuit voltage, and when you short it this through an ammeter, we will short this to terminal where the load resistance is previously connected and measure the I short circuit current here, right? Achha. So what is the experiment? Let me show you. First of all, this one, then this, and let me go to the Is this audible?
Yes, ma'am.
No, ma'am, it's not audible.
Not audible.
No, ma'am.
Oh, no, no, ma'am. No, ma'am. Sorry.
Ma'am, the video is not audible. Ma'am?
Hello. Ma'am.
Ma'am, we can't hear the video sound.
Just wait for a second. I'll call her. Huh? Now it has come. Hello, madam. Hello.
Please.
Madam, could you start from the beginning? It was not audible actually, the video.
Audible?
No.
Is this
Yes, ma'am.
No, ma'am, it's
still
not
not
audible.
Audible.
audible now? Is this audible?
Video is not
No,
audible.
ma'am.
No, ma'am, video is not audible. Only your voice is coming.
Just wait. Audible now? Audible?
No, ma'am.
No, ma'am.
No, ma'am.
Just wait for a minute, huh? Audible? Hello?
No, ma'am.
No,
Video
ma'am,
is
not
not.
audible.
What is happening? Include computer sound. Then this. Audible? Hello, audible?
No,
No,
ma'am.
ma'am.
No, ma'am.
No, ma'am, still not audible.
Aritra sir, do you have the slides with?
Right now I don't have, but I'll try to play from the uploaded video. It is already uploaded, na? So from there I'll
I
just
don't know what is happening. I have run it previously.
just a minute.
Include
Please.
computer sound, then this, then just wait for a minute, then this one, then Thevenin's theorem. It is audible? Audible?
No,
Huh?
not yet.
No, ma'am.
No, ma'am.
What is happening? I don't know.
Ma'am, can you again share? Stop the
Huh?
share.
Can you?
Ma'am,
Yes.
can you stop the share now and then again share it? Then might
Several
be.
times I have stopped it. Several times I have stopped it.
Madam, can you play from the uploaded video? It is there in the their classroom. Under
Aritra,
experiment.
can you do it?
I'm trying to do that. I'm just logging in through the this app. Actually, I'm trying with web-based thing for team, but now I'm logging in. Just a minute. Please hold on. Sriman, do you have the data cable with you? Just get no. I cannot log in also. I don't know what is happening. I'll just leave this classroom and I'll rejoin. Please hold on.
Hello? Hello?
Yes, ma'am.
Let me start it again. Huh? Include computer sound. Speaker to 100%. Then check it whether audible or not.
No, ma'am.
Huh?
No, ma'am.
Still not audible.
No, ma'am.
What is happening? I don't know. Just wait for a minute. Let me check in the uploaded, huh? In the uploaded version. Uploaded Teams. Then files, recordings. Then no, not recording. Very sorry. Files.
Class material, ma'am.
Files. Experiment number. Class materials.
Yes, ma'am.
Class
Ma'am,
materials.
experiment 1. It was experiment 1.
Experiment 1, ma'am.
I got nervous now. Just wait. Audible? It is audible?
No, ma'am.
मैम थोड़ा सा वीडियो का मतलब बढ़ाइए ना मैम 1 minute
हाँ
more than मैम
हाँ include computer sound. Not audible.
No, ma'am. No, ma'am.
What is happening? Not audible. Hello? Audible?
No, ma'am. No, ma'am.
No, ma'am.
I've gone for several options, but it is not. But the first one is running, no? First one was running.
Yes, ma'am.
Include settings, device settings, noise suppression, microphone. Everything is okay. Everything is okay. Camera. Speakers also incorrect.
Hello, am I audible? Hello.
Hi, yes,
Madam?
you are audible. Yes.
I'm trying to play.
Please.
Are you able to see the screen?
Yes.
Yes, sir.
Oh, why it's not playing? Just a minute.
Okay, so now the next
Is it audible?
Audible, completely audible. So for that, the circuit we have considered is this.
It's
like a
maximized
bridge
only.
circuit. It is having 4 arms P, Q, R, S. Now let me show you what are the PQRS over here. Now see here that the two nodes across P, that is A and B. So here this arm is considered to be P, which have two terminals A and B. Next is B and C, across which Q is connected. Okay, so this 2 point we have considered to be B and C terminals, and this is the Q. So let me write it over here. This is P, this is Q.
Simon,
Okay.
your data cable.
Achha. Next is across C and D, S is connected. So C is considered to be this and D, and therefore this one is S. S. And which one is left? That is R, and which is connected across A and D. So A and D, and this one is R. Okay, there should not be any confusion regarding this base circuit. Now one thing is left, that is RL, the load resistance, which is variable. So this one is the variable resistance, which is this rheostat. Okay, and this is connected across CA. So this is C and this is A. And the voltage source, which is considered to be this one is connected across B and D. So let me show you how the connection is being done. So this source is connected across B and D. So we have connected here B and this is D. So this too has been connected like this. Okay. Achha. Now this D and this D shorted, right? Another thing is that A and A shorted, and another B and B shorted, and C shorted, and this C is also connected here. Okay, and this is A, another A terminal. Okay, so this one is shorted. Now ammeter is inserted here with RL. That means across C and A, one ammeter is connected. So this ammeter is here. So this is connected across C and A. Okay, so across C and A, it is in series. Okay, you can see over here it is connected, right? So this is C, this is A point. Through resistor, through rheostat, it is connected. Through rheostat, it is connected, and across this load, one voltmeter is connected. So that voltmeter is coming here. This is the voltmeter we are using over here. It is connected across the load resistance. Here, it is the load resistance, right? So this is all about the circuit connection. Now, what are the run? Run is first, we will set the rheostat at a particular value. Say we are keeping this at 50% value. Let me.
It's almost 50%.
It is almost 50%.
And it is a 100 ohm resistor, and we are at the 50% position, means approximately our RL has to be around 50. Okay.
Okay. This one is the. Okay. So this is 100 ohm resistor. So this. Now let me show you the ammeter reading as well as the
Voltmeter reading.
Okay. So this is noted down. So for which we can calculate the RL, how? VL by IL. Next is our requirement is to have the V Thevenin or V open circuit when the load is being removed and when the load is zero, that is short circuit current. So if we move it to the so in between that also we need to take some readings. So for which we will kept it at 25%, 75% of the resistance value,
and the 100% also,
and 100% also, and for short circuit we will kept it at 0. Okay.
So now we'll short it.
We will short it. Okay. We have shorted. So you can notice it from the voltage value. It is coming out to be 0 since it is shorted. And this is the I short circuit. So everybody can note it down. It is 0.07. ISC, I short circuit is 0.07 ampere. Right? Okay. Next is
we have to now open it to
let me open it.
So that connection we are removing from here. So we have disconnected. Now it is an open circuit.
Open circuit. So you can note it from here. The current is 0. The current is 0.
And open circuit voltage
Yes.
It's fluctuating around 2.2, 2.3 like that.
So you can note it down. It is roughly 2.2 volt for the Thevenin or V open circuit. Now for the complete run, we have taken all the data a priori and you can show it. That is different voltages, load voltages and different load current, for which you can have this. You can have this graph, right? You can have this graph. This is IL axis, this is VL axis. So since VL, IL, we have taken 4 data, you can have this data here.
And then join and extrapolate.
Join and extrapolate. So if we extrapolate here, this side, so this is corresponding to IL equal to 0, and this obviously will be VOC. And in this point, if we extrapolate this, this is Thevenin voltage VL equal to 0. So this is nothing but your ISC. So this 2 point, you will get it graphically. Now let me explain it. How do you verify this? Achha. So RL we have roughly having 43 ohm. That is VL by IL. Suppose we are going
and
to.
that is for 50% setting.
50% setting.
Theoretically, it is 50, and we are getting 43.
So 50%. So now we are going to verify that whether 0.03 ampere load current is coming or not. How we will verify? This will be VOC by RThevenin plus RL. How we are getting RThevenin? That is VOC by ISC. So it is coming out to be 2.3 by 0.07, 32.85. So now VOC 2.3, RThevenin 43.33, RL is 32.85. It is coming perfectly 0.03 ampere. That means it is getting verified. The Thevenin's theorem is verified. Okay. So that is all about the Thevenin's theorem. Verification. Arthur sir, just so what we have done here, we have found out the RL value, which is nothing but VL by IL. So any value of VL and IL out of this 4 data I take, it will divide the VL with IL, it will get the RL value. And RThevenin is VOC by ISC that we have experimentally obtained. So that will give you the RThevenin is equal to 32.85. Now VOC is VThevenin. So VThevenin divided by RThevenin plus RL, it is equal to IL. So it is coming out to be 0.03 ampere. So that we have checked it here. Now what we have already explained to you, and we are going to explain you that. Let me show you. Is the PPT visible to you?
Yes, ma'am.
So these are the results that we have taken experimentally for different 25% of RL, 50% of RL, 75% of RL, and 100% of RL value, right? So in this case, the load current and load voltages are shown, and experimentally we have done the open circuit voltage, that is 2.3 volt, and the short circuit current 0.07. So we know the RThevenin is VThevenin by ISC. So that is 2.3 by 0.07, 32.85. That already I told you. Next is regarding this graph. So for this 4 data, okay, we have drawn this graph. Now this points are joined and they extended, so it will intersect with the VL axis at this point, and in here with the IL axis at this point, right? So this point is giving you the ISC magnitude graphically, and this is the VThevenin or VOC magnitude graphically. Understood? Acha. So this is one thing. Another is that RThevenin is the gradient of this slope. of this slope of this line. So how to calculate the slope? That if you drop a perpendicular here and from this point another horizontal line, they will intersect at this point. So this is the change in VL and this is the change in IL. So that's why it is delta VL and that is delta IL. So what is the slope? Slope is nothing but delta VL by delta IL. Am I correct? Hello?
Yes, ma'am.
Acha. So what is the change in VL? This is 1.6 and this is 1. So 1.6 minus 1.0 and current is 0.02 minus 0.04. Am I correct? So 0.6 minus 0.02. How much is this? This one is minus 30. Isn't it? We told that already aim is equal to minus R Thevenin. So what is the R Thevenin value? Graphically we got, that is 30 ohm. 30 ohm, that is graphically. So experimentally we got 32.85 and now it is 30 ohm, close to each other. So that means it is almost verified. It is verified, you can say. So that's what we have shown. Now intersection with the VL axis, it is giving 2. Sorry. It is 2.25 and in this case here it is near about 0.073. So 2.25. So Thevenin verified graphically and experimentally. Experimentally we got it as 2.2 and it is coming 2.25. So this value 32.85 experimentally and graphically 30. So these two are close to each other and therefore Thevenin's theorem verified. Understood? Any problem to understand this? Hello? Hello?
Yes, ma'am, understood.
No, ma'am.
Understood, ma'am.
Okay. So now you whatever the readings shown to you, you draw this line and get the intercept, y-axis and x-axis. Understood? And verify this whether we are giving this results you are getting also or not from this 4 points. Understood?
Ma'am, we have to use 2 millimeter graph paper.
2 millimeter graph paper. No, any normal graph paper.
Okay, ma'am.
Ma'am, one thing, what is the deadline of this summation, all the experiments?
I think Dr. Bera has given Dr. Bera or Rajdeep sir already posted. I think so.
Yes, ma'am. They told that after 1 week after the end sem.
Oh, after the ends. Okay, fine.
Ma'am, 1 week after or before the exam?
You better ask them.
Ma'am, because as much as I remember, it's before.
I don't know the exact information. You please verify with them only. Arthur sir? Anything more?
No, I don't know actually about the deadline. So better you ask Rajdeep sir or Tushar sir. They'll tell you.
Acha, Malathu Mahesh, do you have any query?
He raised the hand.
Malathu Mahesh. Malathu Mahesh. No query. That's why. Acha. So, Arthur sir?
We can conclude if they are not having any question.
Okay. So, should I stop the recording?
Yes, ma'am.
I'm stopping the recording. Hello.
Yes, ma'am. Stop.